Okay, think about the tech you use every single day. Your search engine, right? Pulling up exactly what you need.
Yeah, or like CGI in movies. Looks so real now.
Exactly. Or even the control systems in your car. What's the hidden engine behind all that? It's often applied linear algebra.
That's it. And we're not talking about the super theoretical stuff, the endless proofs from math class.
No, definitely not.
We're diving into how it works in the real world, taking concepts like vectors, matrices, all that, and seeing how they solve actual problems. It's about the computation, the modeling, what it all means.
And that's what you want, right? To get a solid grasp on something important quickly. So think of this as your shortcut, your deep dive into why this field matters. We've got this overview document on linear algebra, and our mission basically is to pull out the most important, the most interesting bits for you, show you why applied linear algebra is just fundamental today.
Right. So where do we start? The building blocks.
Let's do it. Vectors and vector spaces. What are we talking about here, really?
Okay, imagine giving directions.
Yeah.
You don't just say walk 3 blocks. You say walk 3 blocks north.
Right. Need the direction.
Exactly.
Yeah.
That north is the direction, 3 blocks is the magnitude, the size.
Yeah.
A vector, well, it's just a way to capture both.
Yeah.
Think force, velocity, things with direction and size.
Okay, got it. And the vector space.
That's just the environment they live in. Like a coordinate system, a map. It's where you can add vectors together, maybe combine forces or scale them up or down, make them stronger or weaker. It defines the rules for how they behave.
So it's not just abstract math, it's like describing real-world movement and forces. Okay, so if vectors are these individual arrows, how do we handle lots of them, lots of numbers together? That brings us to matrices, I guess.
Precisely. A matrix is really just a grid, a rectangle of numbers arranged in rows and columns. Think of a spreadsheet, basically.
Oh, okay, like organizing data.
Exactly. It lets you store related data together. But the real power is in the operations you can do, adding them, multiplying them, something called inverting or transposing them. Mm-hmm. These operations let you transform the data, analyze it. Like you could put product features in a matrix, right? Mm-hmm. Then matrix math could help you see how similar different products are systematically.
Okay, so organize data, manipulate data. The overview also talks a lot about solving systems of linear equations using matrices. Why is that such a big deal?
Well, think about something complex, a supply chain maybe.
Yeah.
Or airflow over a wing, loads of interconnected variables.
Yeah, it sounds messy.
It is. And those relationships can often be written as a system of linear equations. Trying to solve that by hand with substitution like you learned in school. Forget it for big problems.
Right.
Matrix methods like Gaussian elimination or LU decomposition. They're systematic algorithms. They let computers solve systems with thousands, even millions of variables. It's about speed and, crucially, scale. You just can't tackle modern complex problems without that scalability.
Scalability. Okay, that makes sense in our data-heavy world. Now, this term linear transformation sounds a bit mathy. Can you bring that down to earth?
Sure thing. Think about a photo on your phone or computer.
Okay.
When you rotate it, or stretch it, or shear it, you're applying a linear transformation to all the pixels.
Okay, I see.
It's a function, right? It takes an input vector, say the pixel's position, and gives you an output vector, the new position. But it does it in a structured way, keeping lines straight, parallel lines parallel. It doesn't warp things randomly.
So rotating an image is linear algebra?
Under the hood, yep. Mm-hmm. Same in robotics, calculating how an arm should move. Or in physics, describing how fields change. It's this fundamental way of describing structured change.
That image example really clicks. Okay, what about determinants and inverses? They sound important.
They are. The determinant is just a single number you calculate from a square matrix. But that one number tells you a lot.
Like what?
Well, critically, it tells you if the transformation represented by the matrix is reversible. If the determinant isn't 0, you can undo the transformation. You can get back to where you started.
Okay, so non-zero means you can reverse it.
Right. If it is 0, the transformation kind of squashes everything into a lower dimension, like flattening a 3D object onto a 2D plane. You lose information, you can't go back. Mm-hmm. This idea of invertibility is key for solving equations and also for things like control systems, making sure a system is stable and controllable.
Makes sense. You need to know if your operations can be undone. Now, eigenvalues and eigenvectors. These always felt like the really deep end.
Yeah, they can seem a bit abstract at first. But the core idea is pretty cool. Imagine some transformation like stretching or rotating space.
Okay.
Most vectors will point in a new direction after the transformation. But eigenvectors, They're special vectors that don't change their direction. They only get stretched or shrunk.
So they stay pointing the same way, just get longer or shorter.
Exactly. And the amount they get stretched or shrunk, that's the eigenvalue associated with that eigenvector. It tells you the scaling factor along that special direction.
Okay. Why is that useful?
Oh, tons of reasons. Analyzing stability in systems, do small disturbances grow or shrink? That's eigenvalues. Quantum mechanics uses them heavily. And in data science, a huge one is principal component analysis, PCA.
I've heard of PCA.
Right. It uses eigenvectors to find the directions in your data where there's the most variation, the most information. It helps you boil down complex, high-dimensional data to its essential features. Super powerful for machine learning.
Wow, okay. From stability to data reduction, that's quite a range. Finally, the overview mentions orthogonality and least squares. Quick version.
Orthogonality just means at right angles. Think perpendicular axes like X, Y, Z. Having vectors or bases that are orthogonal makes a lot of calculations much cleaner and more stable, especially in signal processing or data analysis. It's like finding the most efficient, independent way to describe your space or data.
Okay, like a clean set of directions. And least squares.
That's absolutely essential for real-world data. Because real data is never perfect, right? It's noisy. So if you have a bunch of data points that should form a straight line, but they don't quite because of errors or noise, you can't draw a line through all of them. Least squares is the method to find the line that comes closest to all the points. It minimizes the total square distance from the points to the line. It's a foundation of regression analysis, finding the best fit.
So finding the best possible answer when the data isn't perfect. Got it. Looking back at this overview, the list of places this stuff is used is just huge.
It really is everywhere. Engineering, circuit design, building bridges, control systems, computer graphics, dimension rotation, but also 3D modeling, animation, VR, robotics, motion planning, sensor fusion, data science, AI. We talked about PCA, but also recommendation systems. Basically, all sorts of machine learning models rely heavily on it.
And even beyond tech.
Oh, yeah. Economics uses it for modeling economies, optimizing resources, physics, obviously quantum mechanics, relativity, even environmental science, modeling ecosystems or climate change. It's incredibly versatile.
It's kind of mind-blowing how it's hidden inside so much. So if you had to sum it up, what makes applied linear algebra this game changer?
I'd say a few things.
Yeah.
One, it gives us a compact, elegant way to describe really complex interacting systems.
Okay.
Two, it leads to incredibly efficient ways to compute things, especially at large scale, that scalability we talked about. Three, it helps us find structure hidden in data, patterns, trends, essential features, stability.
Right.
And maybe finally, it's just the fundamental mathematical language for so many computational fields today.
Yeah.
If you're working with data, simulations, control, you're using linear algebra, whether you realize it always or not.
So it's really moved way beyond the textbook. It's the engine, often unseen, but driving so much of the tech we rely on. Search results, graphics, simulations, AI. It's baked in.
Absolutely. It's translating these powerful mathematical ideas into practical tools that build the modern world.
So maybe next time you use some app or see amazing graphics or rely on some complex system that just works, give a little thought to the math humming away underneath.
Exactly. And now that you've sort of peeked behind the curtain at applied linear algebra, where else do you think these ideas, these principles of structure, transformation, and optimization might be quietly shaping the systems all around us?